Good morning, students. How are you? Long time. We have not met, and long time we have not met. As you are all aware of the problems at hand, and in this situation, we have to continue online now. So, what I will be doing is that I will be uploading the videos on each chapter on weekly basis, and you can be able to listen to these videos. I will try and explain the topics as much as I can, sorry, the chapters as much as I can, and then if you have any question, you can send me email, or we can do some video conferencing or any other means to so that you get the concept better. Today, what we are going to look at is we are going into chapter 4, which is the open loop discrete time systems. You are all aware that in the previous chapters, the topics of discrete time systems, Z transform and sampling, and data reconstruction were developed. So in this chapter, this development will be utilized to drive analytical method for the open loop time systems. The derivations are necessary. We are going to drive some formulas just like the previous chapters, and these formulas will be useful also in PQ analysis. So basically in this chapter we'll be looking at three aspects. The first one is the relationship between EZ and E asterisk S. The second one will be the force transfer function, and the third one will be the open loop system containing digital filters. So we'll look at this first one, which is the relationship between EZ and E asterisk S. EZ and E asterisk S, EZ and E asterisk X, EZ and E asterisk S. You all know the meaning of EZ. EZ means the Z transform of a discrete time system sequence, discrete time sequence in EK. If you want to get the Z, if you get the Z transform of it, it will be EZ. And E asterisk S is when you have a continuous time signal and you are sampling it. So when you sample it, you will get E asterisk S. That's if you apply it, if you pass it through a sampler. So in this chapter, what we are going to do is that I am going to show you basically that this EZ and E asterisk S are the same. You will see how it will be. Then later we'll look at the force transfer function. The force transfer function is basically the product of the zero order Hall and the plant transfer function, which you will see later also. Then we'll look at the open loop system containing some digital filters. So the first one, before we go into anything, we need to establish a relationship between EZ and E asterisk S. We need to know what is the relationship between these two terms, EZ and E asterisk S. And how we are going to show it, we are going to show why we need to learn, why we need to understand this, because this will be very important, especially for design of control system, open loop system in particular, and it will really help us to simplify the calculations, and this will also help us to obtain the transfer function very easy, transfer function easily. So we all know this equation, we all learn this equation, that the Z transform of any number sequence is going to be EZ, is EZ, and which is given by this equation 4.1. We all know this, everyone knows about this. So now And we all know the second equation, which is 4.2. When we pass any continuous time signal, either it is in ET, in time domain, or it is in frequency domain ES. If it is, let's say, in a frequency domain ES, you pass it through a sampler, is going to be E asterisk S. So E asterisk S will be in this form, 4.2. So compare these two equations now. If this is the equation for E asterisk S, and this is the equation for EZ, when you compare them, you will see that they look the same. They basically look the same. The only difference between them is that wherever you have Z, you have absolute minus TS, absolute TS here. Just here replace Z and absolute TS. You see this one without the minus. You see that the only difference between the tau is the time period, which can be 1 also. Depending on the time period, can be 1. So it's the same actually. 1 and T is basically the same. So you see that the difference between them is that it's just that when Z equals to absolute ST, when you have E asterisk S, when Z is equals to absolute ST to power ST, then it's going to be EZ. That's just the difference between them. So in essence, when you know E asterisk S, you can know EZ, or when you know EZ, you can know E asterisk S. So when you know E asterisk S, just wherever you have Z, replace it by absolute to power ST, and then you have your EZ. So let's look at the second example, the example 4.1. Look at this transfer function, which is in the time domain, sorry, in the frequency domain. If you are asked to get EZ of this transfer function, that is the Z transform of this transfer function, is going to be this one from the table. Just go to the table. Look at this one, this transfer function. Go to the Z transform table. When you go to the Z transform table, it will be in this form. It's going to be EZ is equals to this term. So now, if you know that EZ is equals to this, then you can know E asterisk S. How you know E asterisk X? How are you going to know E asterisk S? E asterisk S is just going to be wherever you have Z, just replace it by absolute to power TS. You see, this is the same. You see, even this one, look at this Z here, it's replaced by this. You see, the same with this Z also, it's replaced by this. So you see, so that's just the same. So wherever you have Z, just replaced by absolute to power ST. So in essence now, you will understand that the moment you know any one of them, you can know the other one. As simple as that. Okay, now let's look at the pulse transfer function. Consider the open loop system of figure 4.1a. If you look at this open loop system, you can see that there are many components there. You have the sampler. This is the sampler. You have the zero order hold, this one, and you have the transfer function of the plant transfer function of the process. So now, what you will understand here, or what we are going to try and find out here, is that we need to know the transfer function of this open loop system. Why we call this open loop system, why the complete system here is an open loop system, is because there is no feedback. You all know about that. Okay, now, in order to get the transfer function of this, which is CS over ES, isn't it, or CZ over EZ, what we need to do, first of all, we need to simplify it. And how we simplify it is that these two, they are all in S. You can multiply them. These two transfer function of the zero order hold and the plant, we multiply the two of them, so it's going to be GS here. So this one and this one are basically the same. This and this are basically the same. You see, they are basically the same. So now, if I want to know CS transfer function of this system, which is CS over ES, or I'm going to get it in form of the Z transform, so then it's going to be, look at this equation, CS is equals to GS E asterisk S. You see, it's the same. You see, CS is equals to GS E asterisk S. You see here. So now we know that also. When you know this is the transfer function, CS O is equals to GS times E asterisk S, isn't it? So now, if you apply the Z transform on both sides of this equation, CS will be equals to CZ, GS, the Z transform of GS, which is the product of the transfer function of the zero order and the transfer function of the plant. This one will be this one EZ. This E asterisk S also the Z transform it will be, sorry, this one will be EZ. E asterisk S, the Z transform will be EZ, and CS will be CZ. That's all. So now this GZ that you see here is the force transfer function, and this is the transfer function between the sample input and the outgoing sampling instance. Yeah, outgoing sampling instance. That's all. Easy as that. This is also another case of another situation whereby, assuming you have this transfer function of an open loop system where this is the output, and this is the F asterisk S, this is the sampled output, that's from the sampler, and this is the transfer function, the force transfer function, which is the transfer function between the zero order hole and the plant. So when you apply the Z transform here, is the same as the previous case, is going to end up in this form. So where BZ is just the Z transform of BS, and FZ is just the Z transform of F asterisk S. Z transform of F asterisk S, as I said, is just wherever you have absolute power TS, just replace it by Z. That's all. Okay, these are two examples. So in these two examples, what I'm going to do is that I will solve these problems. When I solve these problems, and I'm going to explain them, and I will upload it. I'll upload the video for you in the Blackboard later. Now we will now go to a much more complex systems. Look at these three open loop systems. Look at them here. Look at them here. Look at them here. This is an open loop system, and let's say I want to know the transfer function of this system, which is CS over ES or CZ over EZ. How are we going to do it? First of all, I need to get the transfer function of different components, and then I can combine them together. For example, let me start with this part. Let me get the transfer function of this part. CS is G2S A asterisk S. You see this one? And then I will get the other one. This one. AS is G1S ES. Look at it here. These two. This one and this one from figure 4.3a. So here, if I apply Z transform of both sides, this will be CZ, this will be G2Z, this will be AZ. The same with this one. So now what I need to do, I need to combine this one, 4.15 and 4.16. These two equations, I need to combine them into one, so that at the end of the day, what I will get is that my CZ, replace where this AZ, remove it and replace it by G1Z EZ, and then it will be like this. You see? So the total transfer function of this system will be CZ is equal to G1Z, G2Z, and EZ. So CZ, G2Z, G1Z, G2Z, and EZ. This is the transfer function of this system. As easy as that. So now let's look at the second one, the second open loop sample data system. The transfer function now CS will be G2S, G1S, E asterisk S, which is here. You see? CS is G1S, G2S. Here you have to multiply them because there is no sampler in between G1S and G2S. No sampler in between them. So you have to what? You have to multiply them. You have to multiply the two of them. These two, G1S and G2S, you have to multiply them. That's why they are multiplied here. You know, and then multiply by E asterisk S. You see, multiply by E asterisk S. So now apply the Z transform of both sides. This will be GZ. This will be, because they are all in S, G1S. You cannot get the Z transforms of the two functions and multiply them. No, what you need to do, you have to multiply them in S and then convert to Z. That's what you will do. So why you have this bar here, it means these two transfer functions G1S and G2S you need to be multiplied in S, and then you apply the Z transform of the multiplication, not separately. And then Z transpose of E asterisk S will be EZ, and that's it. So that's all you have. So this is showing that G1, G2Z is the same as the product of the two, the Z transform of the product of, or the multiplication of G1S and G2S. And this rule also applies when you have the Z transform of the multiplication here is not the same as this. And then for the last one, this one, let's go for the last one, this one, which is figure 4.3c. What will be my CS? My CS will be G2S A asterisk S. You see, G2S A asterisk S. This is how it's going to be. But A asterisk S will be G1 E asterisk S, which is A asterisk S will be G1 A asterisk E asterisk S. So it's going to be G1, not G1 ES, but G1 E asterisk, because whenever you are considering this one, it means this one is already sampled. So it has to be E asterisk S here. It has to be E asterisk S, so that when you multiply the two, it's going to be the multiplication of the two in S, and then it's going to be G1 EZ. So this is the transfer function of 4.3c. Now, let's look at a complete system. In this system of figure 4.4, this is the system whereby we have analog to digital converter and digital to analog converter. As I said in the previous class, analog to digital converter, this is just a sampler. This is basically a sampler. This is a sampler. This is basically a sampler. And this one, digital to analog converter, this is basically the zero order hold. We all know zero order hold. This is zero order hold, you see. So now when you have a continuous time signal, then when you apply it to a sampler, it will be converted to a discrete number sequence. The number sequence now, this sequence in the discrete form will be passed through the digital filter, and then the filter is going to process this sequence to give you an output dependent. So this is actually performing the function of a controller. Actually, it will control, or it will change some parameters of the signal. It can amplify some parameters of this sequence to get an output, and this output you need to is going to be the discrete form. Then you want to convert it to the continuous form, you have to use digital to analog so that you pass it to a plant. So that's exactly what you have here. So in order to get a transfer function which is CS over ES, that's what we need to do, because at the end of the day, what we are trying to do in the beginning is just whenever you have an open loop system, try to know how you can find out the transfer function of the system. So now, analog digital converter is a sampler, I said it. Digital filter, assuming the transfer function of digital filter is DZ, and then digital to analog converter, this is the zero order hold, and the plant is this one. So how do you write the equation of the transfer function of this system? We need to know the transfer function of this system. So transfer function of this, starting from here, the most important one actually is this one. CS is GPS MS. Look at it. CS is GPS MS. Let's start from this side and we'll come back. So now, if you have this one, we know that also MS here is DZ, because this is your DZ. Sorry. MS here is going to be the transfer function of the zero order hold times MZ here, the input here, you see, or M asterisk S. This is the zero order, either MZ or M asterisk S, you see. So now this is the same as this. GPS is the same, zero order hold is here, and M asterisk S you need to convert it to MZ. MZ will be, MZ will be what? What will be my MZ? Look at MS will be what? MS will be DZ EZ. It's going to be DZ EZ, or E asterisk SZ is the same. This is the same as EZ actually. This is EZ. It's the same. This is the same as EZ, which is given here, you see. So DZ is here, and this one is here, and this is here, and GPS is here. But this one, so if for example now what they are trying to do here is that get the Z transform of this function. This will be CZ. This one, because it is in S, this is in S, you have to convert it to Z before you put it here, because you have to get the Z transform of this before you put it in 4.24, and this already is Z, so you have to convert everything to Z. To get a transfer function, you have to convert everything in Z. So at the end of the day, transformation will be GZ. So what will be a GZ? The GZ will be the plant transfer function, and the transfer function of the zero order whole, which is a false transfer function. This DZ is the filter transfer function of the filter, and this one is the input, which is a continuous time signal of the open loop system. And that's the equation now describing the transfer function of the open loop system. So this is another example. I will try to solve it, and I will, after solving it, I'm going to upload it for you in the Blackboard. Okay, thank you very much for listening, and hope you enjoy the presentation. Thank you.